This is Lab 11, The Falling Slinky by Sarah Hajati, Lab Section M04. The question presented is, what happens when you drop a slinky? Will the top go to the bottom? Will the bottom go to the top? Will both ends meet in the middle? Or will both ends move together and fall down? So I use the momentum principle to model this motion and try to find the answer. There's a video made to show how a slinky is dropped. And I extracted this data using Tracker. So first, I extracted the position of the top of the slinky as it moves down. The origin is where the professor lets go of the slinky at the beginning. The video is calibrated to the length of the tennis ball, which was found to be 0.0635 meters. I also did the same video and tracked the motion of the ball instead. And as you can see, it's relatively still throughout the video. I tracked both of these data and I put it on an Excel spreadsheet to compare them with the model. I modeled the same motion extracted from Tracker. In order to do that, I took the Lab 8 spring motion data and edited it to include motion with the spring. I calculated the position of the spring by using the momentum principle. And then I got the data of the spring and ball position. If I run it, as it slowly pops up, slowly but surely, there it is. So as you can see, the ball is remaining relatively still and the top of the spring it's at the bottom. These two graphs show the information based on this data. As you can see here in the first graph, the model is the position of the ball and the force that is acting on the ball. So the force is the force of gravity and the force of the spring. And as you can see, even though there is a force acting on the ball, there is no motion acting on the ball. So this graph right here shows the force of gravity and the force of the spring, and the blue line is both forces acting together. So clearly there is a force over time, but the ball remains stationary. Right here, I plotted the position of the ball. The blue line is the model and the orange line is the experimental. They're different because the length of the spring was unknown, so I just used the length of the spring from the Lab 8 lab. As you can see, in both cases, the ball remains stationary. So here is the position of the spring. And as you can see, in both cases, the position of the spring decreases exponentially. There's some difference because the spring constant and the mass and the length of the slinky are all unknown. Thus, the data from Lab 8 was used. So when I play this video, you can see that the top of the slinky moves down to the bottom. And almost magically, the bottom of the slinky does not move at all. This video goes pretty slowly, but by the time the top of the slinky reaches the bottom of the slinky, when that happens, the bottom of the slinky finally moves. So the explanation for this is that although the forces are unequal, it takes some time for that motion to propagate at the speed of sound to the bottom of the slinky. So by the time that information gets to the bottom of the slinky and the slinky this causes the slinky to almost realize that the forces are unequal. It takes a small amount of time, and so that is why there's a delay in the difference in force and in the motion of the slinky. So thank you for watching.